Radiographic Equipment Testing, Part 3. Though not mentioned in this chapter of your textbook, lead apron testing is covered in the ART content specifications and is an annually required test. Each apron should be examined under fluoroscopy for cracks and holes. Improper care of lead aprons, such as folding or throwing it on a countertop or floor, will quickly cause cracks or holes to appear in the apron, leaving the person wearing it vulnerable to additional radiation exposure. You all know they should be hung appropriately. If you look at images of most cracked aprons, they will appear most frequently on areas that are folded, like the image shown here. Now that conventional film screen imaging systems are no longer covered on the ART examination, we're only concerned specifically with digital acquisition systems, including CR and DR. For the purpose of this video, we'll strictly be focusing on the following: field uniformity, erasure thoroughness, and ghosting, intrinsic dark noise, and spatial resolution testing. These are tests that can be performed by a technologist without the requirement of a physicist, primarily by routine visual checks. Unlike older film screen systems, digital detectors are all inherently non-uniform. Field uniformity corrections must be repeated on a regular basis, ranging from daily to semi-annually, depending on the type of equipment you're using. This test can be accomplished by creating an exposure with nothing on the image receptor, then sent to the radiologist reading station for analyzation. When using CR, make sure the plate is erased prior to making the exposure. We need to view it in the reading room due to the high-resolution properties of their monitors and low-light environment that will allow us to see defects in field uniformity more easily. If the pattern looks anything but uniform or there are radiopaque artifacts present, they should be reported to the medical physicist for further testing. Inadequate erasure on a CR system can arise from burned-out bulbs in the erasing chamber of the processor, loss of lamp sensitivity, too short duration of exposure, or a scenario not mentioned in your textbook, extreme overexposure on a previous examination. When this occurs, it's generally referred to as image ghosting. The appearance can be similar to a double exposure, though the actual error of a double exposed cassette was not made by a technologist. The traces of the previous examination end up on the following exposure, causing a repeat to be necessary and increasing dose to the patient. In this image taken from antmini.com, the outline of a patient's neckline and lead marker from an axillary view of the shoulder study are seen in this lumbar spine image taken 2 minutes later. In DR systems, image lag or memory effect may be visually checked the same way. For these systems, it's caused by electric charges that get trapped in metastable states in the amorphous silicon or selenium during an exposure, and they appear when released slowly over time. Intrinsic dark noise is simply image noise that occurs without an X-ray exposure. To test for this, take a CR plate and process it without exposing it to radiation. Examine the image for traces of mottle or noise when comparing it to a baseline image without noise. Spatial resolution can easily be tested by exposing a wire mesh and examining the radiograph for any distortions or unsharpness. This can be the same type of test tool previously used for film screen contact on old systems. Or any bar type resolution test tool will work to allow the radiographer to measure visible line pairs per millimeter. A sharp-edged lead object or a fine slit cut into lead foil may be used for comparison. Physicists will typically use these kinds of objects to obtain an edge spread function or a line spread function.